Hello everyone, this is Sir Aris. Today we will talk about mapping and some applications of conformal mapping. To sketch a graph of a given function, for example, or function generally written as y equals f of x of a real variable x, we need an axis for the x values and an axis for the corresponding y values. So typically, we write the x-axis horizontally and the y-axis vertically. If you have a number x here, it corresponds to some fx here, and there'd be a single point described by this x and fx. We want to do a similar sketch for a complex or a function of a complex variable w. In that case, we need a plane. So here we have two axes, x and y. If you have a complex variable z, um, as an argument in a function, then you need a plane to plot the values of z. So you have a plane to plot z. So you have the x real axis and the imaginary terms y. So this is the z plane. But if you have a function, you need another plane that would describe the corresponding value of the points here uh, on that plane um, with respect to some function or the form of the function. So in that case, you here you already have a two-dimensional uh, plane. You have a plane. Now, if you add another plane, that would give the total dimension as four, which is impossible to draw, even to visualize. So we write down the other plane, the W plane, separately. So we call this horizontal axis U, vertical axis V. Now to plot, let's try so that for you to to be familiar with how we do the mapping of or how we do the plot of a function of complex variable. Let's try it for a real variable first, but instead of writing them in one plane or the axis in one plane, we'll write the axis in two separate lines. So suppose this is the x-axis and this is the y-axis. So they have the same scale. So it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Same thing here. There's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now let's add one more, 10. Okay. Now if on x-axis we have all these points, but in each point we label it. So let's say for this point, let's call it A. For this point, let's call it B. Here we will call C. This we will call D, and so on. Okay, all points here can be labeled specifically according to some variable. So for A equals at point x equals 0, x is 0, that gives us y equals 0. So this is the corresponding A on y-axis. For B, we have 1, 1 squared is 1, so this is where we see our B. For C equals 2, so x equals 2, 2 squared is 4, so C can be found here on the y-axis. And on D, here, x equals 3, 3 squared, that's 9 over here, and so on. So that's how we are going to do our plot for um, a, a function of a complex variable. So you have a z-plane and a w-plane written separately, or drawn separately. So we use a z-plane and w-plane. The pair of points 1z and 1w are called images of each other. The correspondence between a point in the z-plane and the image point in the w-plane, or the point can also be curve or a region, that correspondence is called a mapping or a transformation. For example, consider the function w equals I plus z e I pi over 4. Map the grid of coordinate lines x equals constant and y equals constant into the w plane. First thing we can do, we can setting z equals x plus iy. So we substitute that here. Then we have w equals I plus x plus iy. Um, and then here it's e to the power of I pi over 4. We can simplify that. Cosine pi over 4 plus I sine pi over 4. Okay. Or I plus x plus iy. Cosine of pi over 4, that's square root of 2 over 2. Or this is cosine of 45 degrees. Sine is the same. It's square root of 2 over 2. And then distribute terms. So you have square root of 2 over 2x plus I square root of 2 over 2y, plus I square root of 2 over 2x minus square root of 2 over 2y. This and this. Okay. Grouping terms, real terms and imaginary terms. So you have square root of 2 over 2x, this one, and this one, minus y plus I, terms with I, you have here 1, plus these two have square root of 2 over 2. So we can group them like this. Okay, so in this case, with w equals u plus iv. Here, this would be our u. This would be our v. So u equals square root of 2 over 2x minus y, and v is um, 1 plus square root of 2 over 2x plus y. Okay, and some uh, so we can start here and plot values, but we can also make it easier by adding u and v. So if you add u and v, u plus v would become this and this. So one would have no would we just leave one as one, but the others, let's say square root of 2 over 2x plus square root of 2 over 2x, that would be twice of square root of 2 over 2, so that's square root of 2 times x. But this and this added will just cancel out, so we have a simple term here. We only need the value of x, and then we have an equation for u and v. That's for addition. If we subtracting u and v, we have u minus v equals 1 would still it become negative, so negative 1. But u, this minus this is 0, but this times square root of 2 over 2 minus this is negative square root of 2y. So if we consider x equals 0, if x is 0, this doesn't give us anything, or and something, this doesn't give us anything useful, but this tells us that u plus v would be equal to 1, which is an equation of a line. We normally write as v equals minus u plus 1. So this is similar to y equals mx plus b. If y is the vertical axis, m is the slope. b is the y-intercept. So in this case, 1 is the v-intercept, -1 is the slope. So to put it in proper context, this is x, this is y, this is the z-plane. We map this into a w plane. So you v x equals 0 means for whatever value of y, x is always 0. So that's this line here. Okay. Oops. So this, or whatever this line is, so it's just the y-axis. Okay. That would be x equals 0. Okay. And x equals 0 on the w plane is this line. It passes through v equals 1. So say this is 1, this is 2, this is 3, this is 1, 2, 3, 1, 2, 3, negative, -1, -2, -3. So v equals negative u plus 1. The slope is negative, so it sloped uh, downward, passes through v equals, if u is 0, v is 1, so it passes through here. It slopes -1. It would pass through this u equals 1. So when v is 0, u equals 1. So passing through here. And it's a straight line, so it would look something like this. Okay, so that's our u plus v equals 1, corresponding to x equals 0 line. Now for y equals 0, so if y equals 0, it means that, so this, we can use this. So that's u minus v equals -1. So we can also write this as v equals u plus 1. So the slope is +1. It passes through v equals 1 over here. So when v is 0, u is -1. So the line would look like this. Okay, so that is for this axis here. For y equals 0, it would look like this. So this is our u um, minus v equals -1. We can also try other terms. For example, let's try x equals square root of 2. So that, suppose that this is our x equals square root of 2. So this line here, whatever value of y, x is always square root of 2. Okay. In that case, we have u, we use this, u plus v. So x square root of 2, this is 2, square root of 2 times square root of 2, that's 2. Plus 1, that's 3. So u plus v equals 3, or we can write as v equals -u plus 3. -1 slope passing through v equals 3. This is the v equals 3. It passes through u equals 3. So that's a straight line like this. Okay, pass through here. This is our u plus v equals 3. Now if you try x equals negative square root of 2, then it becomes u plus v equals, so this is negative square root of 2, so this is positive 2, or negative 2, plus 1, that's -1. So it would be v equals negative slope, negative u minus 1. So it passes through v -1 here. And if v is 0, u would be -1. So this is that line. Okay, u plus v equals -1. And we can also try y equals square root of 2. For y equals square root of 2, it becomes u minus v equals, this is square root of 2, this is 2. minus 2 minus 1, that's minus 3. Okay, so for this z-plane, this would be our, suppose this is negative square root of 2, x equals negative square root of 2. For y equals square root of 2, suppose it is square root of 2, then that this would be our line y equals square root of 2. Okay, here on the w plane, it becomes this v equals u minus 3, so positive slope, but passing through v equals minus 3 here. So yes, like this. Okay, that's our u minus v. Ah no, actually no, it's not that one. It's v equals u plus 3. Okay, so if it's plus 3, then uh, that would be for this line. This that would be passing through this, and if u is or if v is 0, u is minus 3 over here. Okay, this is our u minus v equals negative 3. Now let's try one more. Negative square root of 2. For negative square root of 2, this becomes positive 2 minus 1. So you have u minus v plus 1. V equals u minus 1. So it passes through this and this. Okay. When v is 0, u equals 1. So like this. That's our u minus v equals 1. So here, if this is negative square root of 2, that would be our y equals square root of 2. So if you have observed, we are just simply rotating this by 45 degrees. So we are rotating by 45 degrees to get from here, z-plane to this, but the origin would be moved up. So we are moving it up uh, by 1, which is equivalent to I. So if we look at the original form, we're moving it by I and turning it by pi over 4 or 45 degrees. Another example, map the coordinate grid u equals constant, v equals constant into the z-plane by the function w equals z squared. So we write w equals um, z squared, which is x plus iy squared. So in this case, we expand this, so we have x squared minus y squared plus 2i xy, which means that u, this is our u, and this is our I v. So u is x squared minus y squared, and v equals 2xy. So if u is constant like this, so you have a constant equals x squared minus y squared, and a constant equals 2xy. Okay, these two are equations of hyperbolas, so which means that in our w plane corresponding to this, or in the z plane corresponding to this uh, constant lines on the w plane would be hyperbolas like this. Now we show that any analytic function w gives us a transformation to an orthogonal coordinate system, something we need for an application, a useful application of mapping. Um, so if we write our infinitesimal element dz as dx plus I dy, then dz squared is dx, this is the absolute value, dx squared plus dy squared. Also, dw written as du plus I dv. That would be dw squared equals du plus du squared plus dv squared. Okay, so the the square, we'll try to solve the square of the infinitesimal element of arc length. So I'll just write it here, arc length in xy um, plane is ds squared equals dx squared plus dy squared, which is similar to our dz absolute value squared. If we divide uh, or multiply by dw over dw squared, so we can do this. We multiply by divide by dw squared with the condition that we also multiply. So this becomes dz over dw squared, and dw would be du squared plus dv squared. Okay, this is a condition we need to prove that something, or we are transforming to an orthogonal coordinate system. So it doesn't contain, so this one doesn't contain, or which doesn't contain, let me write it properly. This uh, doesn't contain du times dv. Hence, uv coordinate system is orthogonal. So what we can do with this is that if we solve equations u and v in terms of xy, for x and y in terms of u and v, we have the transformation equations from variables xy to the variables uv. Something that we will need this uh, for would be in some applications. For example, this example here, consider the system shown here. You have a system where there's an insulating material around this circumference of a semicircle, but here on this side is it's exposed to a temperature of 100 degree, let's say Celsius. So this is 100 degrees Celsius, and on the other side there's an insulator here. On the other side there's it's exposed to a temperature 0 degrees Celsius. Our goal is to find the temperature anywhere here. Okay, this is very difficult, but the but we look at a simple problem. So we consider the system where you only have a rectangle slab. So suppose this is your rectangle slab in UV uh, coordinate system. Say this is at 0 and this is at pi. At 0, we place our uh, rectangle slab up to some value of u, and then we insulate. We put an insulator here. Let me write that properly. This is an insulating material, and then the material slab is only up to v equals pi, and then here there's another insulator. Okay, so the top part at V equals pi, we set the temperature at 100 degrees Celsius, just like here, but on the top. On the bottom, we set the temperature at 0 degrees Celsius. So in this simple example, right, in this simple example, uh, or not really, uh, just let me write it as a simple problem. Okay, the temperature increases linearly from bottom to top, which means that the rate of change in temperature here would be uniform. The relationship is linear, so we can write T equals the ratio 100 over pi. So it's simply a ratio and proportion problem. Uh, this is 100 up to some arbitrary units. Let's say degrees Celsius per distance. So let me just write here 100 degrees Celsius per distance, so that if you multiply V, if V is 0, then the temperature is 0. If V is pi, the temperature is 100 degrees Celsius. And also, this satisfies the Laplace equation partial squared t partial u squared plus partial squared t partial v squared equals 0. Now let us map the rectangle to the rectangle in the W plane into the Z plane by the function W equals ln of Z. So we have W equals ln Z would be ln re I theta equals ln r by definition plus I theta. Okay, so here this would be our u, this would be our v. Okay, we're writing u equals ln of r, v equals theta. Now at the insulated end of our rectangular slab at u equals 0, this means that if u is 0, then ln of r is 0, which means that r should be equal to 1. Now, if u equals infinite, for example, if here this is set at very far from the v-axis, approaching infinity, then it means that ln of r would be infinity, or that r equals 0. So in the w uh, plane, we have u equals 0. So the u equals 0 here corresponds to this semicircle here. Okay, so our insulation on this end is mapped into this semicircle. And the insulation here, if it's at infinity, gets mapped into this point at the origin. Okay, now our next step would then be to transform. So we now transform Our solution in the W plane, which is T equals 100 degrees Celsius over pi V, to the variables x and y, so that if you have T equals 100 degrees Celsius over pi V, we simply replace V with what we found here. V is theta, but for theta in the xy coordinate system, if you have here xy on the z plane, this is theta, then if this is x and this is y, then tangent theta is y over theta, which means that theta is simply arctangent of y over x.